In part one of this lesson, we went through a little bit of math and a bit of a thought experiment. And we ended up, without too much difficulty, proving one of the first formulas of Einstein's theory of special relativity. We came up with the formula for what is called time dilation. And looking back on that lesson, there were a couple of sort of assumptions we made at the beginning. And then we just sort of stuck with them. They seemed weird, but we said, you know what? Let's just proceed as if these are true and see where we get to. And from that point on, the physics wasn't that hard. We had to know that speed was distance divided by time. The math wasn't that hard. We had to do some algebra, some Pythagoras. We had to factor something. But at the end of all that, we came up with one of the very equations that Einstein himself derived. So what I want to kind of drive home here is that a lot of the stuff in the theory of special relativity isn't based on really difficult physics concepts or really difficult math concepts. It's just based on a couple of weird ideas that you just have to be able to accept. And if you can accept them, and there's good reason to accept them, everything else sort of falls into place. So these ideas you have to accept are what are known as postulates. So a postulate, I like to think of it as an assumption or a belief. So there are two assumptions or two beliefs that we have to have in special relativity. And if we just trust these, everything else falls into place. The first postulate is that the laws of science are the same in every inertial reference frame. And again, remember from our last lesson that an inertial reference frame is a perspective. Reference frame basically means a perspective, a place you can watch from, that is not accelerating. Inertial comes from the word inertia, which means resistance to acceleration. So an inertial reference frame is a place you can watch from, and that place is not accelerating. And this first postulate of special relativity is something that sort of was known or was believed long before Einstein. I think Newton even came up with that or used that. The second postulate is something that's a little more recent. And this came from Maxwell, who calculated the speed of light. And so this postulate is that the speed of light is the same in every inertial reference frame. And remember that light has different speeds in different materials, but the most common thing light travels through is nothing, is open space, a vacuum. And so that part is worth noting. Speed of light, as long as we're in a vacuum, is the same in every inertial reference frame. So two things are the same in every inertial reference frame: the laws of science and the speed of light in a vacuum. This in a vacuum part, I don't want you to get too hung up on that. Sometimes people are like, well, that's kind of contrived, like when on Earth in our daily lives do we ever have an actual vacuum? Light's always traveling through the air or something like that. It turns out that the speed of light through air is almost exactly the same as it is through a vacuum. So most of the time when light is traveling, it's traveling at this speed, and these postulates apply. Okay, so as I noted before, an inertial frame is a perspective or a place you can watch something from. That is moving with constant velocity. An inertial frame is a perspective or a place you can watch from that has constant velocity. All right, so if we take these two things to be true, and we just trust them, and we don't question them, and we follow a little bit of science and a little bit of math, it led us to discover that if two people who are traveling relative to each other time the same event, they will get different answers. They'll disagree on how long a certain event took. This is called time dilation. And there's a formula for it, which looks like this. Okay, so some key things in this formula. Delta TR is the time for the event that's measured by someone in the rest frame. And this word rest frame, remember, is the perspective in which the event basically stays still, or in which initial and final, those moments where you start your timer and you stop your timer, appear in the same place. So that's delta TR. It's the time as measured in the rest frame. Now we're going to look at delta T. This appears the same, only it doesn't have that R. So this is the time measured in the other frame, the frame that is not the rest frame. And one thing I want to note, actually, we'll get back to that in a second. So this v here is the relative speed of the frames. So remember, these two observers could have an argument over who's moving. Each of them feels like they are staying still and the other person is moving. It's not really worth figuring out who's right and who's wrong because there is no one who's right or who's wrong. But one thing they can agree on is their relative speed. Person A thinks that person B is moving at 100 kilometers an hour. Then person B might think that person A is moving at 100 kilometers an hour. They disagree maybe on who's moving, but they both agree that the speed is 100 kilometers an hour. And that's what this v is. It's the relative speed of the frames. And c is the speed of light. Okay, now one thing I want to note about this equation is it is fairly forgiving with units. I can use whatever unit I want for this delta t as long as I use the same unit for this delta t. So I can use seconds and seconds, I can use hours and hours, I can use weeks and weeks, that's fine. I can also use whatever unit I want for this speed as long as I use the same unit for this speed. I can use meters per second and meters per second, I can use kilometers per hour and kilometers per hour, or I can use millimeters per decade and millimeters per decade. So I can use whatever units I want, I just have to be consistent. And part of the reason for that is you'll see, as long as I use the same units here and here, they're going to cancel out. So I'm going to end up with no units. And if you could imagine sort of rearranging this formula, I could take this delta t up here and bring it down over here. In that case, the units here and here would cancel out as well, as long as they're the same. So all the units in this equation effectively cancel out, which means I can use whatever units I want as long as I'm consistent. Okay, so this brings us to the idea of space-time. If two people who are traveling relative to each other time the same event and get different answers, that kind of led us to realize that space and time aren't really totally separate things. They are connected. And the way I like to word this is that changing your position in space changes your perception of time. Changing your position in space changes your perception of time. If you watch one event and you time it, you'll get one time. But if you then watch that same event while changing your position in space, in other words, while moving, you'll get a different time for that same event. Your perception of time has changed by moving through space. In fact, maybe that's a better way to word that. Moving through space changes your perception of time. And that's why people use the word space-time often when we're dealing with special relativity. Previously to these ideas, people talked about space as sort of this region, this area that the universe took up where things could exist, and time as this separate thing that just sort of kept ticking on in the background, always going at the same speed. We often talked about space, we talked about time, but special relativity, for the first time, showed us that space and time are actually connected, and we should think of them as one thing. Now, a common sort of misconception that people have when they know a little bit about special relativity, but not much, is they often believe this. There's different ways people word this, but the idea goes like this: the faster you go, the slower time goes. And this leads people to think things like, if I hop on a spaceship and I spend my whole life traveling really fast, that time will go slower for me, and therefore my life will feel longer, and I'll be able to get more out of it. This is really appealing to people. But that's not how special relativity works. That wouldn't actually happen. If you hopped on a spaceship and traveled near the speed of light, you would perceive your life as going by just as fast as if you had stayed on Earth. And the reason is because if you're on a spaceship traveling at 0.9 times the speed of light, you're not actually traveling that fast from your perspective. We always see ourselves as being at rest. You never see you zoom past yourself. Wherever you are, you're always with you. So you always see yourself as being at rest. So by moving faster yourself, you don't really slow down your own perception of time. It's when other things move past you, times for those things slow down from your perspective. So the better way to word this, I think, is observers measure any clock to run slow if it's moving relative to them. Observers measure any clock to run slow if it's moving relative to them. But someone who is in that clock or moving with the clock would always observe it to be moving at the same normal speed that they would expect. So you can't slow the clock down, at least not from its own perspective, but you can slow down the rate at which you perceive the clock to be moving if it's moving relative to you. Okay, so let's try and do one example here. Bossy the cow is running across the pasture to see her friend Hereford. It's been a while since they've seen each other, so Bossy is excited and running at 0.8 c, or 80% of the speed of light. When Hereford sees Bossy, he can't control his excitement and lets out a massive moo. From Bossy's perspective, Hereford's mouth is open and mooing for 1.2 seconds. So Bossy is interested in an event. She is timing an event. And that event is the moo coming from Hereford's mouth. So if you are in charge of timing this moo, you're watching what's going on, and you're timing how long the moo lasts, what would you be looking at to see when the moo started, and what would you be looking at to see when the moo ended? Well, in both of those situations, you'd probably be looking at Hereford's mouth. The start of the moo is when Hereford opens his mouth. So the event starts at Hereford's mouth. When he opens it. And the moo ends also at Hereford's mouth but when he closes it. Okay, so there's this event we're interested in. We're timing it. It's this moo coming from Hereford's mouth. And we say the moo starts when his mouth opens and it stops when his mouth closes. So who is in the rest frame of this event? The rest frame of the moo? Well, that would be Hereford. From Hereford's perspective, the moo starts and stops at the same place, right at the bottom of his face. From Bossy's perspective, remember, Bossy is running towards Hereford really fast. So when she sees Hereford's mouth open, he's really far away. That moo is really far away. But as she speeds towards him, and then the moo comes to an end, and he closes his mouth, signaling the end of the moo, he's much closer. That moo is much closer to her. His mouth closing happened much closer to her than the mouth opening. So from Bossy's perspective, the moo was sort of moving towards her. Hereford's mouth, where the moo starts and finishes, is moving towards her really quickly from her perspective. So she is not in the rest frame of the moo. She sees the moo as moving. Hereford's in the rest frame because he sees the moo start and stop at the same place. So, we know that from Bossy's perspective, the moo lasted for 1.2 seconds. Now we want to know from Hereford's perspective, how long did the moo last? And special relativity, the theory of time dilation, tells us these will be different numbers because Bossy and Hereford are moving relative to each other. If they time an event, they will get different answers. Okay, so let's look at our formula. Delta T equals delta TR over the square root of 1 minus V squared over C squared. And let's see, so we've got these two delta T's. We got to think which one's Bossy, which one is Hereford. If we're timing the moo, Hereford is in the rest frame. So Hereford measures delta TR. And regular delta T is Bossy. She's the one who sees the moo, the event, as moving. So we have to solve for delta TR. We want to know from Hereford's perspective. So let's rearrange this. I'm going to take this denominator and bring it over to the other side. Okay, and now I get to plug some stuff in. So delta T, that Bossy measures, is going to be 1.2 seconds. V, the relative speed of Bossy and Hereford, is 0.8 c. And that needs to be squared. And then I have c squared in the bottom here. Now, sometimes, well, all the time, you're welcome to, when you sub a number in for V, just put in a number in meters per second. I put in 0.8 times C, but if you want, you know that C is 300 million meters per second, 3 times 10 to the 8. You could multiply that by 0.8 and just put that number in here. And then here on the bottom, you could just put in again 3 times 10 to the 8, the speed of light. You're always welcome to do that. Sometimes you actually save yourself a little bit of work by leaving this C in the denominator and in your speed, and writing your speed in terms of C. Because what's going to happen then is these two C's will cancel out. You don't have to do it this way, but again, it can save a bit of work sometimes. So what does this look like then? 0.8 C squared is 0.8 squared times C squared. And then at the bottom, I still have my C squared. Here, I can now cancel these guys out. And I can crunch through everything I have, and I end up getting 0.720 seconds is delta TR. So let's see if this makes sense. We said observers measure any clock to run slow if it's moving relative to them. That should say them. Okay, so who is the observer that measures the clock moving relative to them? Well, that's Bossy, right? The moo is far away from her when it starts, and the moo is close towards her when it ends, because the moo comes from Hereford's mouth. So Bossy should measure the moo to be slow. She should measure it to take longer than Hereford does. Well, Bossy viewed the moo as lasting for 1.2 seconds, where in fact, from the rest frame where Hereford was, it only took 0.72 seconds. So almost when Bossy's going 80% the speed of light, she sees the moo as lasting almost twice as long as Hereford does. So that gives you a bit of a sense of just how much of an effect time dilation has on numbers like this. So, to recap the lesson. In special relativity, we started out with two assumptions that we just took as being true. The laws of science are the same in every inertial reference frame, and the speed of light is the same in every inertial reference frame. Then, with those two ideas in mind, we were able to come up with this formula for time dilation. And we figured out that if two people who are moving relative to each other time the same event, they will get different answers. A better way to say this is that observers measure any clock to run slow if it's moving relative to them. And it's better to think of it that way than to think the faster you go, the slower time goes, because that is a bit of a misconception people have, and it makes people think that they can actually slow down their own perception of time for events that are with them, which is not true. Then we solved the problem. And sort of the steps we went through here, I think, are important. We first decided, okay, what is the event that we are timing? In this case, it's the moo. And then we thought, okay, where does that event start? Where does that event finish? And then who sees that start and finish as being in the same location? That person is in the rest frame of the event, which means they're going to measure delta TR. The other person is going to measure delta T, and then we can plug numbers into the formula to figure out what those numbers are, delta T and delta TR. Remember that this formula is pretty forgiving with units. You can use any units you want for speed and for time as long as you're consistent. And sometimes it can be convenient to write a speed in terms of c, as then you get this canceling effect. That doesn't always help, and you never have to do that, but it can be useful.